Saxon Algebra 1, Lesson 15. Our topic today is surface area. Yes, it's geometry. Surface area, remember, is when we're measuring not the length of an object, not the area of its flat two-dimensional surface, but we have a three-dimensional object that we're covering with magic wrapping paper, right? So we're going to cover each of the different sides of the outside of the object and add up all of those individual areas to come up with a total surface area. The first example is a good illustration so that we can see what we're talking about. We have a box. I imagine it as like an Amazon-y cardboard box kind of a thing. It's got a front, it's got a back, it's got a top and a bottom, and it's got sides. All right, there are different ways to look at it, but I would consider this the front and this the top and this the sides. And then to help us see its three-dimensionalness, I'm going to put in some dots here. And this helps us see that the front has a corresponding back, the top has a corresponding bottom, and the side has a corresponding side, right? So 6 sides in all. We're supposed to find the surface area of this right rectangular prism. That is a fancy way of saying it's what we call a geometric solid, right? It's an object, three-dimensional object. The word right thrown in there means that everything is at right angles to itself. Oh, excuse me. Everything's at right angles to itself. So that's good news. That means everything is perfect and square. There are some numbers on our picture that John writes like this. So he's helping us see the dimensions of the object. What we can do is recognize that we have corresponding pairs. Let's start with the front and the back, right? To find the area of those two spaces, we're going to use the area of a rectangle, which is length times width. Now what we have to do is carefully decide what are the length and widths of those rectangles that make up the front and the back. Let's see, I need to write this so I know which ones we're doing. The front is 4 by 2. So we'll multiply those together. We get 8. And then we'll double it because we have 2. We're doing the front and the back, right? Now we'll do the top and the bottom. Again, the formula we want to use is for the area of a rectangle. This problem is nice because it's all rectangles. Later it's going to get crazier. Again, that formula is length times width. Now, when we look at the top and the bottom, we have to be careful. The top is 4 by 3. This dimension is 3, right? So that means 4 times 3 is 12. And then when we double that, because we're doing the top and the bottom, we get 24. Now let's do the sides. Again, the shape of those is rectangles. And again, thank you, John, for making this easy. We know the formula is length times width. Again, I'm writing this over and over because in other problems, it's not going to be the same every time. So we will just want to get in the habit of always writing our formula for finding the area of that particular two-dimensional shape. On the sides, it's 3 by 2, right? So that is 6, and when I double that, I get 12. So now I have found the area of each of these different surfaces, the 6 different surfaces that make up our rectangle, and so my final step is to add 1, 2, 3, 4, 5, 52, and now I need a unit, and I go look back at the problem. It says dimensions are in centimeters. So I write centimeters squared, and this is my final answer. Okay. One of the things I like about these problems, these surface area problems, is that there isn't a special new formula we have to remember, right? There is no specific formula for the surface area calculation. What we do is we calculate the areas of each of the flat surfaces and then we add them together. So we're using formulas that we already know. Okay, let's try another one that's just a weensy bit more complicated. I'm going to start with a fresh piece. Example 15-2. This time, our diagram looks like what I would consider to be a Toblerone box. You know that Toblerone candy? I think their packaging has changed in the past couple of years, but it used to come in a cardboard box that was shaped like a triangle, just like this. And I thought that was really cool. And sometimes I would even buy Toblerones for my students for this lesson. But alas, so pretend I'm giving you a box of Toblerone. Old school Toblerone that comes in this kind of, you know what I'm talking about? It's a candy, I think it's Swiss, it's chocolate, and I think it has chopped nuts and little bits of chopped fruit in it. That sounds gross. I'm not a huge fan of dried fruit in my candy, but these are really flippin' good. Okay, find the right surface area of this right triangular prism. Right means that this makes a right angle, everything's square and perfect. Dimensions are in meters. This is my trick for remembering my unit, right? I just jot it down, circle it, and then I'll need that for the answer. Okay, there's numbers on our picture. And sometimes it takes a little bit of work just to figure out what number goes where. So if I'm confused, what I like to do is I like to circle it and make the circle touch the surface that number goes through. Sometimes that just helps my eye understand a little bit better how this information works. Okay, so we're gonna do the same thing. We're gonna make a list of the sides that match, and we're going to just go through and calculate the surface area of each flat surface, and then we'll add them all up. All right, now what I see when I look at this is that this front that's a triangle shape is exactly like the back that's a triangle shape. But each of these other sides, there's the back, and there's the bottom, and there's like the angled part. Each of those, they're rectangles that make them up, right? So they won't be hard to calculate. But each one is going to be a little bit different. So let's start by finding what I would call the front and the back. That's this triangular bit, right? So that's going to be the area of a triangle. And that formula is different. Base times height divided by 2. Now let's see if John gave us all the information we need. The base of this is 3. The height of this is 4. And then we divide by 2 because that's the formula. I'm going to cancel there, change that to a 2 and a 1. So that becomes 6 for one of these triangles, but I have 2. So I'm going to add 12 to my list. Okay, that's the triangles. Now we have to figure out a way to describe these different parts so that we know which one it is. I'm going to think of this as a slide, like a playground slide, where you go up the ladder and come down the slide, and then this is the base of it here. So the ladder part is the area of a rectangle. Whoops, I need to go down a row. I'm running into my row here. All right, so this rectangle back here is like the ladder of the slide. Length times width. Let's see. For this one, it's 4 by, this dimension is 6, right? And that is 24. I'm not doubling it, so I'm skipping that part of the calculation. 6 and 4, right? This 6 is the same as this 6. This is the 4, so that gives me that area there. Okay, now let's do the part that's like the slide that you would come down. That is also a rectangle. So I'm going to use the area of a rectangle formula. It's length times width. This one is 5 times 6. Again, I don't need to write it as a single and then double it. I'll just go right to my answer column. All right. What about the base? And that's this part down here. It's like the grass underneath the slide. Again, area of a rectangle is the formula I need. Length times width. This one is going to be 3 by 6. My dimensions don't look proportional, do they? But that's okay. We know the numbers are right, even if the picture looks a little sideways. 3 times 6 is 18. Now I've calculated the area of each of the different surfaces, and I'm ready to add them up. 1, 2, 3, 4, 5, 6, 7, 8. 84 meters squared. Oh, we got it right. Yay. Fun, right? Well, these have been fairly simple examples because we don't have any rounded shapes in them yet. We've just been doing rectangles and we threw in a triangle. When we throw in some circle-y shapes, it doesn't necessarily get harder. We just have to fuss with decimals because pi enters our lives. Pi, Pi. The other kind of pi would not cause us any problems at all. Example 15.3. Ready? Here comes this picture. A right circular cylinder. Oh, that's like an oatmeal can, right? One of those cardboard things that oatmeal comes in. That's what I always think of. Looks like this. This is called a right circular cylinder. Again, right means that this comes down perfectly even and square. It has a radius of 4 inches, so I'm going to make a note of that. R equals 4. And a height of 10 inches. And John shows us that like this. From there to there is 10 inches. Okay, so I'm just going to write H equals 10. Find the surface area of the right circular cylinder. Okay, remember the trick to this is to get a pair of imaginary box cutters. And since this is all cardboard, we're gonna have a really easy time of it. What we're going to do is we're going to cut with our box cutters. First we'll take off the top, then we'll take off the bottom, and what we'll have left is a cardboard tube that we can pick up and look through, right? It'll have no ends. Our box cutters we're going to use to cut this along the edge right there, and then we're going to roll it out. And this is made of magical unbending cardboard, and it will lay perfectly flat instead of being curled up. And we'll see that this middle part actually takes on the shape of a rectangle. Interesting. I'm going to put our radius into the picture just for fun. That sometimes help us. Sometimes students visualize better when they just have the information. Some students like to see it in the diagram. So I'll do a little bit of both. Okay, so the trick on this shape is to use our box cutters to cut it up. And now we'll start doing our calculations. This, we're going to need the area of a circle, which is pi r squared. In our case, it's 3.14 times 4 squared, right? Because our radius is 4. 3.14 times 16 is the way that calculation will work. So I'm going to come down here and do my multiplication, right? Because 3.14 is what pi is equal to. R is our radius. So here we go. Go ahead and multiply yourself, and then we'll compare at the end. Okay, that's what I got. 3.14 times 16. So I'm going to write up here 50.24. I'm saying that's the area of this top. Okay? Oh, our units are in inches. I just went back and read the problem. All right, I didn't write that down. We have 2 of those circles. They're exactly the same size. So I don't have to calculate it a second time. I'm just going to write 50.24 like that. Okay? Now we're ready to deal with this rectangular bit. I can see that this dimension is 10. But how do I find this dimension? What I have to recognize is that when I took my box cutters and cut along here, the circumference of this circle is exactly the same dimension as the top and the bottom of the cardboard, right? Because it fits, the cardboard rectangle fits exactly around the circle of the top. So if I find the circumference of that circle, that will give me this length. Weird, right? So this is equal to the circumference, which is pi 2r, which is 3.14 times 2 times the radius, which is 4. So I have to do a little calculation to find this edge. Then I'll have to multiply to get the length and the width of the rectangle, right? So I see 2 times 4 is 8. And I come down here and I say, let's multiply 3.14 times 8, right? In order to get that circumference. But before I start to multiply, I go, wait a minute. I just multiplied 3.4 times 16. 8 is half of 16. I can easily find the half of this answer, 25.12, right? Half of 50 is 25. Half of 0.24 is 0.12. So I don't even have to do that multiplication. I can use this calculation to jump me ahead in that one. So I find out that this dimension is 25.12 inches long. Oh, that's kind of cool, right? Now I can multiply that by the 10, right? So it's 25.12 times 10. I know I'm not writing that on the same line. It's confusing, but I'm squishing in here. So it becomes 251.2. Makes sense? And I'm going to add a 0 so I have the same number of decimals in all 3 numbers. That'll just help me add more neatly. My work's a little squished, but that's okay. 8. 2 plus 2 is 4, plus 2 more is 6. 0, 0, 1. 5 and 5 is 10, plus 5 more is 15. Carry 1 more, and it's 3. 351.68 inches squared is the total surface area of our big can of oatmeal, let's just say. All right? So this is a good example of a slightly more complicated surface area problem because once you start throwing circles in, we have to calculate not only the area, but also the circumference in order to get the length of that cardboard. So it gets a little more involved. We have one more of these problems, and again, it's a little more involved yet. John likes to, he calls it incremental growth. He likes to take us baby steps forward in our work so that we don't get overwhelmed, but we do keep getting harder and harder problems. He does a good job of making nice baby steps. Okay, this is an old-fashioned mailbox standing on end. And P.S., I consider one of the fun parts, I'm not a huge fan of these problems, but what I do like about them is I like drawing the picture. I think it's kind of fun. Okay, so this is like an old-fashioned mailbox. On its side, right, here's the little door that you'd open and your mail would lie on the bottom and the flag would be down here. That's the kind of mailbox I had growing up. Now we just have little squares. All right, this kind of shape is confusing because we don't know how to find the area of this shape. This will do the cardboard box cutter trick. Looks like a bulging mailbox, doesn't it? There. That looks better. this is a lot of confusion because we don't know what that looks like. So John gives us a different picture that he tells us is the area of that base. So what he's saying, mine's not proportional, but he's saying that this surface here looks like this detailed picture. And this is the way the detail looks. Again, mine's not proportional, but it doesn't need to be. So now what we see, oh, and he tells us that a solid is 10 feet high. So height equals 10, and our unit, it says dimensions are in feet. Okay, what we want to do is find the surface area of all the surfaces, right? So we can see there's a top and there's a bottom, right? That's gonna look very much the same. And then we're gonna use our box cutters to open this up and make a big flat cardboard rectangle out of that. So first, let's work on the top and the bottom, all right? It's made of two pieces. First, we've got a rectangle, right? So for that, we know we're gonna need a length times a width. Here's the rectangle part, it's 6 times 5. Notice the way I'm laying these problems out. It's not exactly the same every time, but it's close because what I do is identify what shape in the picture I'm working on. I identify what basic geometric shape that is. I find the formula, I show my calculation, and then I show the answer. That's the basic form I want you to use to organize your work so that it's not just mad scribblings all over the page, which can work too, but it's really hard for someone else to follow. So that's why I like to make these charts, really. Okay, so length times width, 6 times 5, 30. Now we need to find this part. Again, we're working on area, so I want to find the area of a half circle. Well, that is pi r squared. That's the area of a whole circle, and then we have to divide it by 2. Okay, so our radius is 3, so it's going to be 3.14 times 3 divided by 2. Make sense? All right, so what we'll do is, oh, it's r squared. Sorry, I forgot to write that down. So now over here in my calculations area, I'm going to go 3.14 times 9. 3 squared is 9. So I'm going to multiply that. And I get 28.26. Now I have to divide this by 2, right? Because we only want a half circle. Well, that's really easy to do in my head. I see that is 14.13, right? Half of 28, half of 0.26. Easy. Okay, so that tells me that the total area of this base is 44.13. That's cool, but I have 2 of them. So what I have to do is add another 44.13 to my calculation. Now I've taken care of both of those, right? Okay, good. Now I'm ready to do my magic cardboard. The reason it's magic cardboard, remember, is because if you had a shape like this and you cut it with box cutters, it would probably be curvy and it wouldn't lie flat and it would be annoying. I don't want to annoy you with these problems. I want us to have nice, smooth, flat cardboard that readily assumes the shape of a rectangle. So that's what ours does. We take our box cutters. Let's cut right here. We'll start cutting right here. It's always easier to cut at a crease, right? And we'll notice that when we lay our cardboard down, this is that cut edge. So then we're going to go along a few inches and we're going to have a fold in it, aren't we? And then we'll have this part is the curving bit, and that will be all of this, right? We know that this dimension is 10. because the height is 10. So that means this dimension is 10. So when we lay our cardboard flat, it means that dimension is 10. This dimension is all the way around, right? It'll be 6 plus 5 plus this we're going to have to figure out separately, plus another 5. Right? So see how I've sort of, this isn't even a crease. This is like a curved bit on our cardboard, right? So this is the 6, this is the 5, this is the part we haven't figured out yet, and this is the other 5, right? So I'm making sure that I'm mapping between my flat cardboard and the original diagram to make sure I'm getting all the numbers, all the measurements right. Now, this part of the rectangular cardboard is the part that went around the curve. So we have to find this measurement and add that to our list down here. That measurement is the circumference of the half circle, right? Let's see, circumference is pi 2r. We're dividing it by 2 because we only want the half circle, and we remember, oh yeah, we can simplify this calculation because the 2's drop out. So all we have to do is multiply 3.14 times 3. Not 3 squared, we don't have to square it. We just have to multiply 3.14 times 3, and that will give us the number to add in here. So 3.14 times 3 is 9.42. That number goes right here, right? So I'm going to write 9.42. Now we have to add all these up. Let's see, there's a 10, 19. It looks like it's 25.42. Right? I add the 5 and 5s, that's 10. I add the 6 and 9, that's 15. 15 and 10 is 25. Then I tack the little 4, 2 on the end. However your brain likes to do that, I just explained to you how my brain did it. Now we know that to find the overall area of this whole cardboard, we have to multiply this dimension, which we just spent a lot of time figuring out, it's this, 25.42 times 10, which comes out to 254.2, and I'll add a 0 so that there's the right number of decimal places. Now we're ready to add this up. I got a little squishy here, but it's okay. I'm going to just cover that up so that your brain won't accidentally get confused by those numbers. Here we go. 3 and 3 is 6. 1, 2, 3, 4. Decimal. Remember that when we're adding decimals, we line up the decimals. That's why I added the 0 there, so that they would have the same number of decimals. 3 4s is 12. 8, 9, 10, 11. Oh wait, I got thrown off, didn't I? 4 4 4 is 12. This is 5, 9, 14. And then I carry the 1. See, I wrote these too squishy and I confused myself. But my final answer is 342.46 feet squared. And remember that surface area is a kind of area, so it's always squared. Areas are always squared. Sometimes students get confused because it's a three-dimensional object and they want to make it cubed. We're not measuring the volume of it. We're only measuring the outside surfaces. This is the correct answer. I consider this to be a very hard surface area problem. There are a lot of pieces going on there. But that is our final answer. Remember that all of this side calculation business that we have to do, that is an important part of the problem. If it helps you, if you don't like this, if you think it feels cluttery, you can make what I call a work area. so that that's separate from the rest of your problem. Some students feel better doing that, kind of like walling it off. But please don't use scrap paper. Please don't erase this. Please don't feel like, ew, that's so messy and gross. That's part of the problem. We need it to be complete. All right. Let me just show you the practice problems. You're going to do one that's a rectangle. Okay, that's easy. It's just all length times width. This one looks very much like the Toblerone box. This one looks a little different at first. But remember that if you stand it up on its end, it's just like this one that we did, right? This is the oatmeal box. So don't let this one freak you out. It just mentally stand it up. And then this one is like the last one that we did, where you have to, you see the three-dimensional object, but you have to get a map of its base so that you can add up the components. All right? This is very much like the one we just did last, except ours was a rectangle and a half circle. This is a triangle and a half circle. All right. Hopefully this is all stirring up lovely warm memories of last year, and you're like, yeah, I can do this. We will be doing these for quite a while, so settle in and enjoy the ride. Thank you. Goodbye.